I have to introduce the concept of magnitudes. Now, first, let's talk about rational things, like fluxes. So you have a source of radiation, like thermal blackbody or synchrotron or whatever, and it's going to have a flux as a function of frequency. And if you integrate over all frequencies or all wavelengths, you get total luminosity. Now, that's what usually you measure, how much flux you get at a given frequency or wavelength, whether it's radio or optical, it doesn't matter. And radio astronomers have introduced the unit of Jansky in honor of the first radio astronomer, and its value is given here. So first radio sources were measured in kilojanskys. Now people are talking about microjanskys or even nanojanskys. So technology marches forward. So this is flux density, specific flux per unit frequency or sometimes per unit wavelength. And to get the total power, you have to integrate over a spectrum. But usually you don't integrate over the entire spectrum because you can't observe from zero wavelength to infinite wavelength. There is always some finite bandwidth over which you do that. In visible light, it's different filters. In radio, there is, again, bandwidth and so on. Now we come to magnitudes. Sometimes they say that magnitudes are invented by astronomers to keep physicists out of the field because they're so utterly irrational. But the historical reason for them is ancient Greeks, being scientifically minded, quantified the brightness of stars. And they decided that with the naked eye, good vision, dark sight, like a Greek island or something, not too much wine, you can distinguish 6 different levels of brightness among the visible stars. And the very brightest they called 0th magnitude or first magnitude, and the faintest were 6th. Now, turns out the human eye is not a linear detector. It's actually a logarithmic detector. And the steps of 1 magnitude correspond not to a linear shift by a certain amount, but by multiplicative shift. And 1 magnitude corresponds to roughly 2.5. It corresponds precisely to 10 to the 0.4 power. This was quantified in 19th century. So another way to look at it, if you're minded like an engineer, a magnitude is minus 4 decibels. It's 10 to the minus 0.5 power. So it's a logarithmic scale, and that means there is a 0 point. And that 0 point is where things get really weird because, in principle, it can be anything you want. So before we can actually do absolute calibrations of things, it was just decided as a convention that Vega, which is one of the brightest stars in the sky, will have magnitude of 0 regardless of which filter you use. Now, spectrum of Vega is not flat, not at all, but that was the convention. So the 0 point varies with wavelength. Then to make life even harder, some other people introduced different 0 points. Let's not even go there. But at any rate, what happens is when you have a detector like CCD and taking a picture through a given filter like a V or blue or something, you're integrating flux over a certain wavelength regime, and that total amount, you take log of that, multiply by minus 2.5, and add the 0 point, and you got the magnitude. So it's upside down logarithmic scale with a weird unit, and even weirder 0 point. But a handy way to kind of get some idea is that for visible magnitudes, for Vega, 0th magnitude is roughly 1,000 photons per second per square centimeter. And if you like Janskys, that's about 3,500 Janskys. All these things are tabulated in the proper places, so if you actually ever need to do it, you look it up. So how do we use this? Since this is a logarithmic measure, it has to do with the ratios of fluxes expressed as a logarithm, right? It tells you how much is one thing brighter than the other. And because there is that minus 2.5 log 10, that means that a factor of 100, which is 2 orders of magnitude, will be 5 magnitudes. So it's don't confuse it with orders of magnitude. Astronomical magnitude is 0.4 orders of magnitude, right? And it goes upside down, so the higher magnitude means fainter objects. Now, sun is the brightest source on our sky, and it has apparent magnitude of minus 26 and change. That means it's really, really bright. And the very faintest things that we can observe with like Hubble Space Telescope are 28th, 29th magnitude. And you can figure out how many orders of magnitude that is. Be a good thing to work out, say, during a section. Okay, now let's make life a little more complicated. Introduce the absolute magnitude, which is now a measure of luminosity, not flux. Magnitude is measurement of flux. It doesn't tell you how far something is. It's just how bright it appears to you. But you'd really like to know how luminous things are, so that therefore you need to know how far they are, and use the Stefan-Boltzmann formula and all that. But before we could actually calibrate any of that, people figured out, well, we can use magnitude, so we can introduce the concept of the absolute magnitude. And absolute magnitude is an apparent magnitude your source would have if you put it 10 parsecs away. Why 10 and not 1 is anybody's guess. It just makes life more complicated. So the formula is given here. Obviously, you have to be proportional, right? But then there is 5 times log of the distance. Why that? Because it's the square of the distance that matters in the square law. It's minus 2.5 times 2, so it's minus 5 log of the distance. And then there's this plus 5 offset to account for the silly 10 parsec 0 point. Be that as it may, the conversion is given here. If you put our star just like sun, 10 parsecs away, it will have apparent magnitude around plus 5. So pretty dim star, but still visible with the naked eye. So Vega, which is 0th magnitude, forget how far the Vega is, but it's not very different from 10 parsecs. So roughly speaking, how much more luminous is Vega than our sun? Anybody has a guess? Think about it for 1 minute. And now we can express the distance as a function of absolute and apparent magnitude. Why do we do such a silly thing? Because you can calibrate for certain type of object. What are their absolute magnitudes? Like say stars of a given type. Because of their color or spectrum, somehow you know that kind of star we have established is 365 times luminosity of the sun, whatever. And so by measuring their apparent magnitudes, you can infer from the known absolute magnitude how far something is in crazy units of 10 parsecs. And that difference is called the distance modulus. Sometimes you encounter that. So ideally, you'd like to know absolute luminosities as in solar luminosities or ergs per second or whatever, and distances in parsecs or centimeters. But instead of that, we use these somewhat strange units.